Okay, fantastic. Okay, so continuation of the lecture on power saving techniques. We had this big nice table that we're gonna revisit throughout the lecture to show you all sorts of various knobs and optimizations one can do in a system. Before we go there, I kind of found this fun article about future computer chips may be made out of honey. If it sounds like an April, first joke, it was actually pretty interesting because, as you know, here we're talking about digital techniques, digital design of digital systems, but of course, there's a lot of people looking how to build essentially analog equivalents of computation, including inspired especially by neuromorphic computing and kind of analog neuron modeling and things like that. And it turns out that honey has these kinds of nonlinear hysteresis properties that you would, when you pass the current through it, that would actually mimic the behavior of the neuron. So they actually, out of all sorts of materials, these researchers found out that honey kind of best behaves when polarized. So you can imagine like flex organic substrate sandwiches with honey doing some kind of computation, right, in the future, all in the spirit of very low power kind of intelligence at the edge. And actually that market is now basically planning to explode in the next 5 years. It always used to be there's going to be some IoT kind of a revolution in the last 15 years, but never really kind of truly materialized except for a few types of devices. But as the technology scales and our capability to understand digital systems, we're trying to pack a lot more computational intelligence and data gathering and processing intelligence into not only data center, but really edge devices. And so these are becoming more powerful, but we also have limited battery resources in a lot of these cases. So a lot of these low power techniques, which used to be, like you would only do in a watch or something 10 years, 15 years ago, or maybe you start translating phone. A lot of these techniques are coming back, inspired by these platter of systems on chip that people are trying to build with the various low power techniques. So a few assignments. Assignment 3 is due today on Wednesday, 4/13, that's tomorrow. And assignment 4 will be out shortly after that. And then we have a quiz, number 3, on Thursday in class. And that will be largely on what we covered under SRAM topics. So there are a few lectures there. So take a look at those, see kind of what are the most important points you need to remember. And those are likely going to be in the quiz. Okay, why optimize leakage, right? Leakage is one of the sources of power consumption, as we discussed. You have switching or active energy and leakage, and then you have, in certain cases, like short circuit power dissipation, depending how the fan out and fan in is designed in logic gates. And this is an example from about 10 years ago, but just to show you that, since in the last lecture, we talked about DVFS, right? Dynamic voltage frequency scaling. This is like, let's say, an experimental IA32 core, which has essentially, the cache with its own memory system. Then you have a logic with its own supply system. Then you have the logic with its own supply, so that you can decouple the SRAM supplies from the logic supplies, because as we've seen in the last lecture, these scale differently in terms of performance, and also constraints in the memory SRAM for the retention. You can't scale as deep as you can the logic. And then you have kind of the power control unit that essentially determines what happens with this power management unit that determines what happens when you gate different resources, like, for example, gating the floating point unit, right? So you have different registers that, as we'll see it later, go through different power states so that you can traverse both the active regions. And if you look at here, it's basically frequency versus voltage, right? So you get, as the frequency goes down, of course, the power goes down, right? So, and you can scale the logic by a certain amount, but as you see here, the memory is always at a higher. So you can maybe go from like 1.2 to like a half a volt, really like 0.5, 0.6, while you can scale the logic much more deeply towards sub-threshold, right? Of course, in practice, so what you get is this type of curve, because it's not about scaling power, it's really about scaling the energy, right? Because you have a finite battery or you're trying to minimize the energy dissipation for a task. So in practice, you're interested in how much it takes to compute a task, right? So even if you can afford to do the task slower, you still care about the energy per task, right? So one of the things that happens here is that as you scale the volt supply and you nicely scale the dynamic energy, right, leakage basically increases at lower supplies. And why? Because you need a lot more time. You see how the frequency scales here, right? You need a lot more time to perform the computation. So the closer you're to the threshold, you basically need more time incrementally to compute what you want. So then you're integrating all this leakage power, right? And so if you're very close to threshold, you basically, your delay kind of goes to infinity, right? So therefore, you are integrating a small amount to infinity. It beats the dynamic energy that you save, right? So there is kind of like a sweet spot here. And obviously, what sets this sweet spot is the choice of the, let's say, threshold of the transistor, right? I can choose to have a leakier process where my threshold is lower, right? And therefore I can push this to the left, but I'm also pushing it up because it's overall leaking more. Or I can use a higher VT process and basically push this a little bit to the right. But obviously then my my dynamic energy will also increase because I have to upsize the gates because I have a higher threshold, right? So the C will go up. So those are all things one can play with when they're designing the processor. But what is key to know here is what's the activity, right? Because what I'm plotting here, you know, what they measured on why they built this experimental processor is because it's not that easy to know what the activity of these units is when the actual workload is running. You can always go and say, oh, you know, 25% is the average if I'm toggling on data, but then you know that the deeper the logic gets, the less activity you have on many paths, right? And we talked about last time about some of these like conditional zero gatings and things like that. But ultimately, it's not even about any given unit. It's about how frequently are these units fired when an application is running on that, right? And so to really be able to understand what this curve looks like, you need actually to run a bunch of benchmarks on the machine as you're scaling and kind of average out all these behaviors. Okay? So what people have done is basically that. You know, this was just the DVFS side of the story, right? When I'm active, what I'm doing, and how deeply should I scale the voltage before I start paying too much for the energy, right? One more important point here is that this curve, this rise here, heavily depends on what your threshold is. So now, and exponentially depends on it because leakage is exponential, right? In threshold. So if you have threshold variation, the closer you are to this, the more unpredictability you have in this region here, right? So it could be for a nominal threshold, it could be here. For 10% different threshold, it could be over here or way over here. So you have a window that or you have, let's say, a distribution of these curves as you have a process across millions of chips, hundreds of thousands of wafers that you need to kind of tune across, right, to be able to find the right spot. So that's why on the processors, we have all sorts of power monitors right now, the whole active DVFS system that will tune end processor binning by performance, AKA threshold, etc. And so you're able to kind of, on a per chip basis, figure out where you want to be in that space, or roughly what this curve looks like. That's only the active part. When application is running, it gives you these statistics, so you can kind of estimate what to do in the active part. But application also has idle times. So this is, for example, a CDF of idle events versus duration. And this was done kind of several years ago in like an AMD, I think it was Bulldozer. So you basically run all these are not full applications, but they're basically kernels like web browser, some thread, or text editor, you know, they have a whole bunch of representative things. And if it's a general purpose processor, you can imagine that there's a very widespread for heavy duty DSP tasks to some kind of general purpose integer type computations. And these are all different. But you see that essentially, you know, some events with relatively low frequency are very, the idle times are very short, 1 microsecond, 10 microseconds. And then you have essentially kind of a smaller amount of them, let's say maybe, you know, 20% that are above a few tens of microseconds, right? And so you're trying to figure out which one of these you can leverage to turn down the processor during these idle times. Right? So last lecture, we talked about clock gating, for example. That's one technique. So you save on active clock power, but you pretty much don't save on anything else because you're still leaking, the thing's still on. And so understanding these profiles and the overheads associated with entering the power off state, whatever that is, and coming back is really key to that control strategy. So I'll give you a few examples of that. Yeah.
Oh, what does CDF decide?
CDF is just a cumulative distribution function. So it's just like you're starting looking at how many events have, you know, cumulatively event duration above a certain amount, right? Yeah. Okay.
And for DVF,
oh, this is dynamic voltage frequency scale, right? So you're essentially, as you see here, you're scaling the supply, and as a result, you're slowing down your machine, right? This is all assuming that slowdown is acceptable, right? You're willing to wait for the task to finish, and you want your goal is to lower the overall energy spent per task. For example, you know, the fab builds a process with some threshold voltages, some on currents. That process is going to serve both high performance applications and low power, and you can adjust things a little bit, as we'll show. But ultimately, let's say you have more performance at the nominal voltage than you need for the application, right? How do you save energy? Well, you scale the voltage and you accept that the frequency slows down. We also talked about parallelism techniques, right? That where you don't, if you have area to trade, you don't have to compromise the performance, right? You will just basically parallelize the units and then be able to go and have the same throughput as before at lower energy, but you still give something up. That's the area, right? there are all these different trade-offs, but this is for like one design. If you're willing to compromise on the throughput or the completion of the task, you can save energy as long as you don't get too greedy, right? If you get too greedy, you go into this zone, you're actually not saving anything because you're spending everything on leakage, right? So it's important to kind of stop at this point. But due to threshold variability, you don't actually know where this point is because there's a whole distribution of curves here from chip to chip. So you have to bin it and be able to kind of sense where that onset is. Okay. So we're going to go through some number of techniques. As I mentioned, someone at the beginning of everything, let's say you're working in advanced technology team in Intel, what they do is anytime new process node is designed, they port a whole bunch of circuits, even to the level of processors like this, and they try to work with the fab to determine for those typical architectures, what's the right blend of threshold voltages, for example, to use, right? How should I know how many voltages, threshold, or types of transistors to have? Every additional type of transistor is extra money that you have to throw at the process. And you want to see with what granularity you'll be able to kind of optimize the design for the range of applications that you're interested in, right? That's harder to do in general purpose fabs, like let's say TSMC, a little bit easier to do in fabs that only do their own designs like Intel, right? But, then on the other hand, big fabs like TSMC, they have, few large customers that they care about. They tune the process to them, and then the rest gets what they get, right? And they have to deal with that, right? So at design time, there are some number of techniques we can do. So we're going to go through some of them. Let's say pick the number of thresholds that will make your life easier, or balance the leakage and active power. Of course, we're going through these like as a singular examples. You really need to do this holistically. So people have very sophisticated power modeling tools that have all these knobs, can run the architectures, and ultimately do tape outs to figure out what the variation distributions are. But we're going through these techniques like standalone, but they're all orchestrated together in the end, right? So for example, what you can do and what more actually tools that do today, if you do have a standard cell library with different types of transistors, for example, RVT, LVT, like regular VT, low VT, high VT, right? That's a typical 3. And you may have UVT or a few more, right? And so what the tool will do, given the timing constraints or a range of corners, design corners you want to operate over, it will basically go and replace, for example, detect that this is a critical path, right? So it will put all low VT devices there because let's say that's what's needed to meet that critical path. But then we'll detect that there are a few other paths that are not critical. The logic depth is less, right? So it will go and swap the high VT devices in there as much as possible to be able to recuperate the positive slack that you get on the critical path and basically trade it for lower leakage. So this used to be like kind of a manual custom process of figuring it out, but since synthesis tools have advanced, you do these things nowadays. As long as you have a richly characterized library that has tells the tool what to do, the tool will do it. So as I said, typically you would get 2 to 3 thresholds. Sometimes, you design more, 4 to 6, and then prune down. Essentially, what you're gonna do in different process technologies, you can achieve these thresholds in a different way, either through doping or through the work function kind of engineering, which is what's happening more in high-K metal gate structures. And you basically get a spread of up to 10x between these things. So it actually pays off quite a bit, because if you think about it, in many designs, many of the pots are not non-critical. Right now, why is that? When we know that from sizing stuff that we talked about, that the optimum is that all the pots are critical, right? The reality of it is that you can't minimize on a small logic depth pot. You can't minimize the transistor size to 0, right? It will be some minimum size below which you can't go. It's just not an available device, right? If you try to do logic optimization, let's say with standard library devices that you have, you won't be able to do it because there are some minimum size logic gates that has to be there, right? And so once you go and optimize the design for that, then you go back and add these multi-threshold devices so to minimize the other energy sources you can, which is now the leakage, right? Okay. What else can you do to the standard cells or logic cells, flops at the transistor level? Well, you can try to use longer channels. Now, this is a bit of an old thing, right? Because in FinFETs and beyond, everything's going to be the same exact thing, right? But this is what people have been doing for a while, essentially playing tricks like something like this, where again we have our switching energy that I've shown you, right? And switching energy decreases as a function of gate length or as well. Right? You basically minimize your capacitance, but the leakage current increases, right? Increases in this region exponentially. So again, you're playing this trick of an exponential versus something that's, let's say, quasi-linear, right? And you basically say, okay, what if I back off from my smallest gate length in certain pots, which are not that delay critical, right? So I can increase by 10% the gate length, but I drop my leakage by 35%. Right? So that's a good deal. And okay, this is like an old process node, like 130 nanometer. It gets better if you go to more scaled nodes, because of course with node scaling, I get higher leakage anyway, right? So that curve, it gets even nastier. Right? And so you can do that selectively as long as this is allowed in your process from the patterning standpoint, right? If the uniformity of the transistors is more important in the process, like we get in the FinFET, you can't do it, or in the more advanced nodes. But this is kind of the trick that people play, exactly just playing this sensitivity of one type of energy versus the other. Another example is basically doing the poly bias, right? So if you have, this is 28 FDSOI. So if you have a 24 nanometer wide poly gate, you keep the pitch of the polyfins, you just expand the length of the gate. Right? Now, this does present additional challenges, and I mean by that, you're going somewhere from 20 effective, whatever, 30 to let's say 40. So you get almost a decade kind of on leakage, right? By changing the threshold voltage by this much. Now, this does present a challenge to lithography, right? Because now you need to deal with these poly jogs here, right, in corners. So optical proximity correction has to work harder, and you can't keep doing that in much more advanced nodes. But this is one example in the older node. Another technique that you can do, and effectively, it actually nowadays becomes even more important, because if you don't have the length anymore, the only thing you can do in a logic gate is add a stack. It's not quite the same, right? But that's your only tool to be able to kind of effectively change the leakage within the logic gate, right? So we're going to talk about some stack effects and how that affects the leakage. So the stack effect is basically that if you have one device versus two devices that are both off, right? Your leakage effectively reduces in such a device, right? So you have this for the same voltage essentially that's being applied. In this case, let's say this is the bottom part of the logic gate, right, which pulls up. So the pull down part is off, right? And so if you take a look at kind of what happens really here is that because leakage is strongly VDS dependent, right? That's the first factor. You have your upper device as Vint increases, that's this internal node, right? And why is there Vint in the first place where there's leakage current going through this, right? So something is gonna accumulate on this internal capacitor here. And so once the currents get balanced, right? So this device, as Vint increases, its current sharply drops, right? There's also additionally kind of threshold modulation happening here because you're connected to the ground in the substrate, right? So this one is like really severely affected. And then it's balanced with what happens with this device. As initially, it's basically conduction is zero because there's zero VDS across. And then it slowly increases as the VDS increases, right? So at some point, these two things cross and that balanced current establishes essentially this potential here. And what is essentially the net leakage, right? So if you see here, basically, if you applied kind of VDD to either one of them, you get like a 5x larger leakage, but ultimately when they're stacked, you get less, right? Now, of course, since they're stacked, if they have the same size as this guy, they will have effectively lower on current. So you are compromising something here, right? And so we'll see in the next slide what it is. But you can get with a number of stacks, you can get basically orders of magnitude reduced leakage current. And now in the nodes where the only thing you can use is like a single transistor size, like a fin, right? And you can only increase the width by more fins, but you can't change the length. This is the only way for you to essentially do something within the logic gate, right? Okay. Now, as I mentioned, it does come with a penalty, right? So let's say this is my inverter, right? I want to have an effective drive or effective fan out, whatever, proportional to this size of the pull down. But so if I split this width to 2 to minimize leakage, right? I'm maintaining the load. So whatever is the previous gate looking at this sees the same load, that's all fine. But I'm actually I now have 1/3 of the current drive in this gate, right? So that may be fine if I'm okay with extra delay here in the gate, right? And if we have pots with big margin, basically with a lot of positive slack, I may use that up by replacing it with this gate. But ultimately, if I'm still trying to optimize something, I could also upsize these guys to, let's say, 1 and 1.5. But in this case, I have 3x the loading, but the same drive current. And you can kind of see that there's an optimization here, right? How much you're loading the previous stage, how much you're dropping the drive current. So you can really optimize, if necessary, the full path to a target slack that you want to have in your design, right? Okay. So the next technique, these are all like design level techniques, right? So we can do in older technologies, change the length. In newer technology, or do the stacking. In newer technologies, just do the stacking to change the kind of let's call it effective channel length, although it's stacking is not quite that, but like effectively minimize the leakage through sizing in the gate. We can also swap in the thresholds. These kind of have similar effects of trading eye on for eye off in a gate, right? And you have to do that very carefully within the design so that you still meet the design targets, right? On all the paths. And then we also talked about choosing multiple thresholds to swap that in different places, right? Now, going back to the beginning when we started, it's not all about just a single logic gate or a delay on a, or how much slack you have on a logic path in a certain logic unit. It is what is the activity of these logic units, when are they used when an application is running? And what's the dead time between these events that you can maybe use to power things down, right? And so those are kind of the optimizations that are in the sleep mode, meaning in the idle time, where you have a chance to minimize the leakage. But some of the choices you make there also affect your runtime, right? Because anytime you choose to go into sleep, especially if you're doing that with power gating, like we're going to talk about, to minimize the leakage, you have some overhead going into that and coming out of it. And we'll show kind of the diagrams of that. That overhead affects your runtime, also affects your energy overall. So if you're too zealous to optimize, you may end up with more energy spent and slower runtime because you're frequently getting into sleep and getting out, being very ambitious about what you can save in that small amount of time and not aware of your overheads. Right? It's kind of a similar thing as overdoing it as like deep pipeline, right? Where the more you do it, the less performance or frequency boost you have because you have a setup time and clock to queue, right? In a flip. So similar thing is here, but just more at the system level, right? So here is kind of some nomenclature that people are using, and this is just an example from, let's say, general purpose processor type of conventions. Various ASICs or system on chips have different names for all these things, but just so you're aware of it, when we talked about DVFS, right, dynamic voltage frequency scaling, we're talking about the processor working, right? So it's the processor is performant, it's running an application, depending on the desired throughput of that application or your user mode or whatever the OS wants to do, you will be cycling through these performance states, P states, right? It also may depend on the OS figuring out how much battery you have left and trying to optimize or inactive tasks, whatever, to keep them just like lightly running. So it will cycle through these performance states. So those are all our DVFS states. Now, in these pockets of time between the events, depending on how fine of a granularity you have on your sleep, and we'll talk about hierarchical power gating. We talked about clock gating the last time, right? You could clock gate a single pipeline stage, you could clock gate the whole unit. It all depends on how your clock distribution is done, etc. So depending on all these things, you have a variety of sleep states, right? And the definitions of what each sleep state entails. And so here is a little kind of decoding diagram that we can go through just to see, for example, what's happening, right? So let's say active state, C0, right? That's all of these states that are encompassed with DVFS. Okay, so you have core clock on, PLL is on as a clock generator for that core. This is all core level, but you can imagine, as we talked about in a previous lecture, there in multi-core systems, there's even yet another level that manages the threads and which core is performance core, which core is the energy efficient core, and how the tasks are allocated among the cores, right? So there are all these levels of hierarchy that the OS has to consider, right? But this is like a core view, right? A single core. Then you have L1, L2. And you have then the last level cache, right? And typically the last level cache is shared among all the cores, right? So L1, L2 is kind of the cores domain, and L3 is going to be shared. So that one is going to be harder to turn off when we start going there, right? And so then you don't have the wake up time because you're active. Idle power is basically not there, except that even when you're working, you're leaking, right? But you're active. It's a blend of leakage and static. And the transition energy is not existing because you are active, supplies are stable, everything is happening. You do have some tracking how you're doing DVFS. There's going to be a change in the supply voltage. So, but that's normal. And so now if you start going into like a C1, let's say C1 core voltage could be, let's say, a little bit reduced. Core clock is, and of course, you need this core voltage to be still at some level because you're going to have the, for SRAM, let's say retention, right? For flip-flops, you also have retention. They need certain voltage because they're essentially cross-coupled inverter in the end to retain whatever's in the register. Right? It will be lower than for memory, but still it's going to be something, right? So you can lower a little bit the supply, turn off the clock. PLL, you can't turn off because it takes a long time to basically establish a stable clock, right? And this mode is really like fast. I want to very quickly go in and out of this at like sub-microsecond type level. So you need to keep all the caches populated and active. And so the wake up time is very quick, right? I just need to basically enable the clock again and maybe adjust the supply a little bit, right? The problem is that the idle power is the highest because we're leaking all this time. I've been able to reduce the leakage a little bit with voltage scaling on particular units if I do that, but it's going to be something. And of course, there's going to be some transition energy as small overhead just from me introducing kind of the clock gating type circuits throughout the design. They add more overhead to the clock distribution. Now in C3, we can start turning things off a little bit more aggressively. So you knock the PLL. That's going to be basically some tens of microseconds, let's say to load, maybe up to 100 microseconds. And then you flush the first level cache, right? Now, here you need to deal with, so it's some wake up time that's associated with, let's say you start missing, data is gone from this L1, L2 cache. So as you wake up to go do stuff, you basically need to start fetching. And so you have early misses in that zone. So that's like a penalty on when you actually start really running the operations, as well as the energies. You're fetching now bits from L3 to L1 and L2, right? So that energy overhead is basically a little bit bigger. And then, you know, if you now go to, let's say, C6, which is essentially a power down of the core, meaning the flops are down. So you had to scan out the state from the registers. And then on a power up, you have to back scan that stuff in to be able to bring it up in the known state to resume. That takes time, right? So that's even bigger time. But you collapsed everything, so your leakage is basically better. And then finally, you know, you have kind of the states that are called package states, where at the level of the whole package, meaning you including L3 or everything is just like getting shut down, right? And of course, you are reducing the package further, but because now you have kind of a lot of power domains completely off, as we'll see later with virtual power rails, when you target, you basically need to replenish all that capacitance, right, to be able to establish back the supplies. And that's quite a bit of energy at the level of the whole package. So you better be careful how often you get into this state. Essentially, transition energy always has to be smaller than your idle power, or the delta between, you know, this idle power and this idle power times whatever the time is that you're going to be in sleep. It's kind of a relatively simple optimization. And if you look at, none of these things are like rocket science. There's just so many of them, right? And choosing the right blend and the right dynamics of it is really what the challenge is here in the controller. Okay. So a little bit more detail what's actually happening here, right? So when we have a clock gated system, right, we're inactive, the P state changes, this is very quick, right? We're just gating. We have the idle time, come back pretty quickly, continue to run, right? So this I can address with this applications that have relatively short idle times, let's say down to a microsecond, maybe even more aggressively if I actually want to at the lower unit level. It just also depends on the latencies of the controller as it's executing this kind of clock gating schedule. On the other hand, if you look at the power gated stuff, there are all these overheads, right? So first of all, the controller has to decide to do the P state change. While it estimates all that from the application, can take about 100 microseconds. You have to do the cache flush. That also takes a bunch of time. You have to save the state of the processor. That's about 100 microseconds. You have to restore the state. That's another 100-ish. Then, depending on how complex your power network is and how much capacitance you have on your decoupling capacitance, basically on your virtual rails, and the package inductance and all that, you basically have around 100 microseconds to come back up. And so once you add all these things up, you pretty quickly see that stuff that's like less than half a millisecond to a millisecond is not really worth it. Okay? Then you go back to this application diagram that I've shown you, and you can kind of bin the events and see where you can save. And then there's a lot of, let's call it algorithms or strategies to try to figure out when is a good time to go to sleep. Given all these overheads, keep in mind, as the application is running, you're kind of trying to predict the future. So it's not easy. Something's running. Even if I know that application well, there's going to be some other thread. I need to kind of know how it's all going to play out. And of course, if I knew all that, then I don't need to compute. So I need to have some like simple predictor, right? Based on the past events, caches, whatever the activity is, I can predict, am I going to go soon to idle state or not? And if I do, how long should I basically, how long will it roughly be, right? And maybe that's based on the previous power state. So there's a lot of different optimization techniques in these predictors so that you can try to hit this balance. Because if you're too greedy, if you go into every idle state, whenever there's a small signal, you're going to be paying, once you're in, you signed up for it, right? You're basically down for at least half a millisecond, right? So if you got triggered wrong here, you're wasting your performance or slowing down your thing, first of all, by a half a millisecond, which is huge. Second of all, you're paying a lot of energy here on coming back from it. So if you didn't save a lot here, then you're actually wasting energy in your system. So you have to be very careful how trigger happy this policy needs to be. Right? So kind of from the lower level, once you decide to do this, right? Okay, you're going down the power state. There's kind of a sequence of events that you want to do, right? So the first thing you're going to do is basically stop the clock. Then you isolate the inputs. Right? and then you save the state. So that nothing can change whatever you decided to freeze. It's very important not to skip an extra cycle there and miss, because then you have to kind of figure out where you were when you're entering the state. Right? And then you basically have a reset, and then so you have a known place where you are, and then go to the power gate. Right? And after the power gate period, you basically release the reset and start restoring the data. Go back to couple the inputs and then start the clock. It's like a sequence of things that needs to happen in that particular order, and it's all executed basically by the power controller. Now, oh yes.
If you save your outputs there already, why do you need to reset before?
So when you save the outputs, the reset is just like a good thing to apply so you know where everything is in your system. It's a very predictable thing from which then you know what happens, right? Because if you are saving the state, things could be in some weird mode. But if you do a reset and then the power gate, then think about, let's say, simulating the power gating situation, right? You want to simulate it only from one state, because that's easy. I verify it in this state, and then I know that it always works. Okay? If I don't do that, I will have to simulate or validate or verify the transition from any state to a completely power gated thing, right? But what does that any state mean? It means certain state of all the capacitances in the system, everything. So when I'm power gating and I need to know, for example, we'll see later when we talk about the exact footer and header devices and how it's done. You can't just like power gate like I've shown here, drop it, right? And because that will create huge CDVDTs, right? So huge transient currents you may not be able to handle. So what you need to do is basically ramp it, right? And so how do you know how much to ramp? Well, you need to know what is stored where, right? So that's why it helps you to be in a known state. So you can know, okay, in this state, I know exactly what's happening in my system and what the starting point for my transient is. So I can time it and apply the proper ramp techniques and things like that. Yeah, it's a good question. Of course, this also depends on what are you actually gating, right? We talked about just the power states of the processor, but you've seen that there's like C1 through C7, right? So in all of these sub things, you can decide to go and gate off different resources, right? For that, you need kind of essentially a hierarchical network, right? So in this case, you have kind of hierarchical power gating. Let's say you have let's say this is a whole basically package system, right? So you can gate off the package. You can gate off the core domain from, or the CPU domain from the memory subsystem, right? In this case, you decide that you keep always the memory on, except when you're in the package state, right? And this is, remember, this was like our L3, right, for example. Okay. And then locally, you can have basically additional power gates, let's say for vector, floating point, for the Mac unit, or you decide that integer core is kind of most frequently used, so maybe you gate it off only globally, right, within the chip. But you also have other options, whether you want to kind of have these local power gates or expose everything to kind of the core system, right? It's kind of a matter of floor planning and what you want to do in terms of where the power controller is actually stored, right? If you have many cores and each core has its own power controller, And then there's a global controller in the chip. You need the synchronization between all of these power controllers, right? Maybe more efficient because the global power controller is not overwhelmed by following everything, right? It only needs to follow kind of the core status, and then the core can decide internally what to gate. But it's also whatever every core locally does still impacts your overall system. So you need to be careful how you balance these things so that the local controller doesn't get overly zealous, and then the global controller kind of can't track what's going on there, right? Because the global controller still needs to distribute the threads to all the cores and decide what to do. Okay. Now, when you go about then realizing these power gates, there are several of these things you need to worry about. And as we mentioned, so there's power gates, and then there's where is the controller, right? And not just whether the controller will essentially power the gate on or off, but as we discussed a moment ago, what is the sequence in which it's going to power the gate? Is it going to do the ramp by, for example, controlling which segments of the power gate are going to be turned on or off in order not to rush all the current from or into the design? Then there's a choice of also just the overall size of the power gate, right? So I nominally want it to be very large because I want it to be zero resistance for ion. But that's a huge size, and it also leaks. Right? When it's off, that thing also leaks. I'm not saving as much on leakage. So there is some trade-off there that you need to play. Plus, if it's very large, remember that there is this transition energy overhead. When I'm turning on and off the power gate, I have to drive it with something, right? So it burns some CV square energy just on switching itself, right? Gate and all the parasitic capacitances. So you have to be careful what the size is to balance out this leakage versus active energy that the gate consumes. It's also that once you add the R on during the active state, your new VDD that the logic gets is lower, right? So what ultimately happens is, let's say I have a design that nominally works well at 1 volt, right? And hits my peak performance that I want at 1 volt, right? If I add a power gate, let's say power gate adds a droop of 100 millivolts, right? What I effectively need to do during the on state, I need to jack up my VDD to external to 1.1 volt, right? Well, that just increased my power by 10% in the on state, right? Because it's VDD times delta V for the internal swing, but my VDD got higher, right? So I need to take that into account because globally, yes, I'm saving on leakage with power gate, whatever that balance is of the on off, but I'm in any working state, I have to keep my VDD higher than in the non-gated design. So all of these things kind of need to be balanced out and taken into account. It's kind of the same thing in regulators, in LDOs, right, where you pay for the overhead, but there you're trying to do it so that you can move the supply, let's say like in DVFS, and also to be able to provide a kind of a more stable, less noisy supply, right, to amortize some of the glitches and transients. So there are all these trade-offs that you have to do in the power system. As we talked about, you need to manage the slew rate or the rush current, right? And you do that by kind of sequentially turning on the power gate. And then you also have to do state preservation. How do you add the mechanism to read everything out of the flops or not? That depending on the design. So in general purpose processors where you're essentially scanning in and stuff anyway, and being able, for debugging purposes, you want everything to be basically scan based so you can quickly recover the state. This is not an overhead. But in other designs, let's say you got an ASIC where you don't really feel the need to scan every single flop for performance because the scan adds overhead. If now you need to kind of restore the state there in that computation, this is kind of an extra capacitive overhead that you're adding to your system, right? So that you have to trade off for the recovery. And yeah, we talked about this sleep-wake transitions, overheads that are involved. So some of the insights is that you don't really need both a header and a footer, right? So what is a header? That's basically a device that gates at the pull-up stack, right? And at VDD, and the footer gates ground. Okay. So one is enough, but it's really about the distribution of R on and this trade-off back to what's the effective size, right? Because if you're using, let's say, a PMOS header, right? You know that for same R on, it needs to be bigger in some technologies. In more modern technologies, that has been alleviated a little bit, right? But, and then there's a question of, well, if you don't do a header, you're still charging up some portions of the capacitances, right, through the stacks that you're reaching anyway. If you have a footer, you have other considerations as well. So you have to balance kind of the two and make a choice depending on the types of logic you have. Do you want to, for our technology, do you want to use a header or footer? We talked about this extra line resistance, wide sleep area we talked about. Yeah, one of the things, and this goes back to kind of your question about state and things like that, is adding this additional R on also causes, of course, causes the droop. So to judge what that droop is, you need to find the worst case transition vector in your design to be able to know how much to margin for, right? As well as the finding from the reset state what is the actual transition requirement to be able to go successfully in and out of the state. So we talked about how the sleep transistor degrades performance. So you need to jack up the power supply. And then we'll show some layouts of how these virtual rails are done with the normal rails. You have extra metal that you are dedicating to the virtual rails, because now you don't only have VDD, you have VDD and gated VDD, right? And VDD needs to be routed up to a certain point. The rest is gated VDD, right? But in these areas where both exist, you're basically double paying for the power supply distribution, right? And once you power gate, that virtual rail is actually going to come down because of the leakage. Leakage is going to discharge whatever's there, so that's lost, right? Okay. Several choices, just like we have for normal logic gates, right? Size is not the only knob you have. You can also choose the high VT versus low VT device, right? And so, okay, if I want to gate the leakage, I want that device likely to be high voltage so that it itself has low leakage, right? It doesn't allow leakage to get into my logic circuit. But of course, for a given voltage, when it's active, right, for a given VDD, it's going to have higher R on. So that impacts my active state, right? And so you have to essentially couple that with whatever is the peak on current to see what is the droop that you're getting in your application. So here's some basically example where people looking at various ways to drive the gate, right? So if you do like a multiple threshold adjusted threshold device, you basically get this type of power reduction, but you get kind of the largest virtual supply bounce, right? Whereas in other cases, if you're using kind of, let's call it the low VTH, but you do different techniques. For example, here you're doing what non-boosted sleep means, like vanilla power gating. So either on or off at the VDD I give it, right? Nothing special. I still get some power reduction. With boosted sleep means that I'm overdriving it when it's down, right? So that I try to minimize the leakage. And then instead of that, I can do the high VT, but then I'm kind of compromising a little bit on the droop. Now, where do you put these things? Of course, we said it, they're actually pretty sizable. If you look at the, they're actually ginormous if you think from the transistor perspective. This is an example. This is a whole ALU. So the PMOS and NMOS, in this case, they used, I think, both a footer so both a PMOS and an NMOS. And you see this like almost 9% of the overall design are the sleep cells, which are shown in yellow, right? As tracks around your design. So it can get pretty big. And so that also factors in your overall kind of optimization. Now, as we mentioned, if you look at the standard cells, you can have, yes?
Isn't the ELU like the most type of most repetitively used device in the microprocessor? So why would we want to power gate it? Because it might be switching on and off.
Sorry, which one?
The ALU. Isn't it like very frequently used in like all operations in a microprocessor? Somebody use the ALU in some form or other. So why would we want to power gate?
Unfortunately, the answer is no, right? Because like, think of it as like, even if you're doing, I mean, I showed you the curve of idle events, right? So that actually shows there's quite a few things that run that are not using the processor at all for good chunks of time. But you can think of things like what happens on a cache miss, right? You only have a certain depth of instructions you can run, even in like a out of order machine, right? And so, you basically start running stuff. If you have a cache miss, you have to stall to wait, right? So a stall means ALU is not running, right? That's even the finest granularity, right? But then there are some applications that are just basically, let's say they're doing some computation, then they have to go fetch a whole page from the memory. They've done it partially through the RDMA or like a DMA mechanism, but it's not quite enough. Still a lot of data to transfer compared to the amount of computation that you need to do. And you're not able to swap another thread, right? So then, yeah, your ALU is sitting idle. Now, that's the job of the thread schedulers, is to see, is there more applications or more threads in the given application that I can, in the meanwhile, overlay to keep the ALU active. So indeed, I want to keep it as active as possible, right? But it may just not be there in the application, the type of parallelism you do, or the instruction level or data level parallelism, things like that, right? It may just not be there. The other thing is that, there are cases in especially lower power mobile devices where you're just not using stuff, right? Nothing's running, but you want it to be lightly on so that when you want to use it, it actually performs, right? It doesn't take 10 seconds to boot and do a task. Then you need to do context swaps between things that are happening in the processor. So you need these power gate states to kind of bridge these idle times.
Just a quick follow-up. So if ALU is not the most frequently used, then what would be the element in the processor which is?
I think most used is, is kind of a really a question, right? Like, because if you say by, let's say, most used normalized by the number of transistors it has, I would still say, yeah, it's LU. But is it used 100% of the time? No. So if it used on average 10% of the time, then if I don't optimize, or 20%, then if I don't optimize for these 80% of idle events, then I'm wasting energy, right? That's what we're trying to do, right? But ultimately, you know, memory cache is used all the time, right? It's just that there's more transistors there, right? And so you are definitely always trying to read something. Otherwise, you know, unless you're doing like a systolic array or something where really or in place computation, right? You are constantly fetching something from at least L1 and then on a miss from L2 and then less frequently from L3, etc. Right? So the further you go out of kind of the core computation, the less you're using the resource, less frequently. But you may be using it for a bigger chunk of time, as I said. Let's say from DRAM, you're often fetching a page, right? That's a long string of data coming in a burst, right? And then you do some stuff. Yeah. Okay. So, you know, even at the standard cell level, as we said, there are kind of two types of cells that we talked about. Like, let's say you have an HVT cell, right? In a library, you have an LVT cell in a library. We already talked about how you would swap these in and out of your design. Okay, in an LVT, you get about, let's say, in this example, let's say 2x boost, right? In performance, but your leakage is like 70 to 100 times that larger, right? So you would use these cells only in very active pots that are basically the most critical. And then one kind of compromise you can do kind of at the standard cell level is to basically gate, right? So you don't get as much performance because you're introducing this additional device in the end pull down. But these were the times when, you know, NMOS was way better than PMOS. So, you know, if you add one more NMOS here, it doesn't hurt your performance that much in terms of the overall effective fan out. But you're able to basically roughly achieve the performance of the high VT gate in terms of leakage. So that mix of kind of a high voltage transistor within the cell that has all the other LVT is kind of like a new thing, right? We talked about these two previously, where you either have all HVT or LVT. In this case, you have an additional sleep signal that basically turns it off. This is not a global power gate. This is just like a local thing that you can play kind of in your design. Of course, there's overhead. This still costs some area within the cell. This signal needs to be routed everywhere, so you need to have that basically in your state, right? And there are just different ways. How do you optimize the layout so that you can kind of compactly add this one transistor here? In terms of the transistor grid, as we discussed, you do have some overheads in terms of the rails. So normally, let's say if you're using, let's say in this case, metal 4 for VCC or VDD and metal 4 for VSS, you reserve metal 3, which is a lower rail for the virtual ones. So now your power gate is basically connecting between the VCC and the virtual rail, and then you're providing a local horizontal track for the virtual VCC, and then the same thing for the VSS. So now in this region, because you're doing this because you know all your cells follow a certain orientation, so you are actually doubling in this region the number of tracks between VCC and virtual VCC and VSS. Right? So you have to take that into account. Now, we talked about kind of the overheads of entering the power states, exiting the power states. So roughly what's happening, and this goes back to your question about like, okay, are we active all the time? Well, you're active, but then in some period of time you're inactive, and you want to minimize this leakage power here. With ideal power gating, transient, yeah, I could go immediately to power gated, save energy, and wake up, and then just recover some of my state. But in reality, just from the electrical standpoint, not even the logic, the misses in the cache or anything like that, I really need this ramp, right? And these ramps will be essentially different ramps on the turn off versus turn on, depending on what my logic on that reset state that I get in my memories and my registers. So if the idle time gets too short, you see what happens. Basically, you essentially never really even leverage. You never even get turned off completely, right? You're basically just trying to get there and then immediately come back up. So you don't have any savings, but you have just the penalty of discharging the virtual rails and turning on the power gate. Okay. So as we talked about, there are these different states, but if you're really gating fully the core, means your virtual supplies are collapsing, registers lose the state, right? So there were tricks to basically say, okay, well, maybe to save that registers, to avoid the timing penalty with saving the registers and then restoring them, you saw that was about 100 microseconds each, right? So to shave off that overhead, and also because registers are actually pretty power hungry, or in terms of the overall effective capacitance in the design. So if I keep them on, right, and I shut down all the logic, because there's basically more logic capacitance, right, but it's activated less frequently than the register capacitance, but register capacitance is always clocked, right? So in terms of the balance, what leaks more, it's the logic. Just like the memory has even the lowest activity factor, right? And it leaks the most, right? So you have this kind of progression where you say, okay, maybe I keep the registers on. I will shut the clock off, of course, but like just keep the VDD on, just like I keep the VDD on SRAM, so that I can keep the state, and maybe I lower the VDD a little bit, like we've seen in the C1 state. And then I can much more quickly come back because I'm only power gating the logic and I don't care about the state of the logic, right? So that's basically this technique. The downside is, of course, there's some leakage in the registers, and also you need this second supply. Remember on the previous one here, we only do this kind of in the region where the power gates are. And then once you move out into the core, you only have basically the gated supply. There's no need to run an additional one. But with this technique, you actually need to run another supply where all the registers are. And so that actually adds kind of the density of the metal requirements, or effectively, if you look at it, increases your impedance on your supply network, because you're now splitting the overall impedance between two. And then if you look back at who has the largest active power, it's the registers. So you need to provision that supply actually to be fatter as it comes in, or lower impedance. So those are the trade-offs that you're introducing, right? So not only is an extra supply, but it's an extra wider supply, right? So that's something to keep in mind. And as we mentioned, you can lower VDD in sleep. Of course, there's additional things there like noise, process variations. We've seen all of that on SRAM, how that affects basically the retention voltage. So it's all the same stuff here. It's just a different state preserving device. So we mentioned already the scan in and scan out. So essentially, you need to be able to scan out the state from all the flops in the pipelines. And now you need also, so this is now also a compromise, is that how many of the parallel scan chains you have, right? The more parallel scan chains you have, the faster you'll be able to scan out the state. But then more pins or more readout resources you need. So if you need to multiplex or effectively serialize the scan chains, it takes you a long time to get the stuff in and out of the design, right? So that's an extra overhead that you need to consider. And then, you know, there are also, just like we talked about standard cells, having either HVT or LVT or some mix, right, that are power gated. You basically have the same thing here. You can in a register, right? So you can do a hybrid register where, again, these dark ones are all the critical path things that basically affect the clock to queue and setup time. So these are all low VT. Right? So when the flop is active, you want to minimize those overheads. But then in the sleep mode, you're basically gating off these two things, which are the leaky main path inverters that are going through the flop. So these are LVT. So gating them with high VT. And then your retention, your feedback is basically HVT, right? So that stays on a dedicated supply, right? But because it's HVT, it has lower leakage overall, right? So that's kind of like a compromise. Yes, I have a dedicated extra supply, but at least when I'm off, I will leak less because the only thing that's on in this flop is basically high voltage feedback devices. Right? Obviously here, you know, these when they're on, they still have some resistance here. So it's not like you're getting it for free as you introduce this gate, but that's basically the compromise. Okay, so we covered a whole bunch of things today. Threshold, multiple thresholds per cell, or cells with different thresholds, then multiple thresholds per cell, both in the logic and in the flops. Then power gating at the logic gate level, at the register level, at the block level, and hierarchical across the whole core and the whole processor, right? And then what are the overheads associated with that? And then really ultimately at the application level, you need to decide what is the frequency, what is the blend of applications you're designing for. If you're building just an ASIC, systolic deep learning chip, it's only running one algorithm that's basically built in, only doing multiply accumulates. You can kind of, if it's an inference chip that just gets a stream, you will know exactly what to do because there's a very fixed static schedule of operations. And you only need to balance, for example, between, if it's a sensor-based thing, how actively you're collecting the data from the sensor, right? And then power gate in the inactive events, turn it full throttle when there's actually collection and compression, whatever you want to do. Right? However, if you're building, let's say, a GPU chip that needs to go in a day, or an accelerator that goes in a data center where now you want to scale out to, let's say, a massive 1,000 processor or 1,000 XPU system that cranks out a huge application, then you need to look at a blend of neural networks, right? For example, the recommender models, NLP, all of these things have different structure. They have different memory requirements, even across beyond the package, right? Actually across, even beyond the node, across many nodes. So you need to look at what's the memory transactions. What's at that point, what becomes important is how many computations can you hide behind the communication latency? You're not only going to hit the memory, you're going through first, second, third level switches to be able to fetch all the data. And so you need to balance out what computation you're doing, how much you're idling, waiting for data, because you're not able to hide the communication from computation, and see if you can embed some of these methods into. In general purpose processors, it's even worse, because the application diversity is even bigger, right? So what people do still is, that's why you have server class cores that go in the cloud. They get profiled on typical cloud-based applications, right? Virtual machines, databases, that type of stuff. And then you have clients like this one in the laptop that have users grade applications, right? And all these get profiled and basically kind of put into these power controllers. Okay, any questions, comments? Okay, next we're gonna do, Bora is gonna do a lecture on energy optimality. This basically looks at, if you could choose VDD and VTH, how do these exactly trade off, and how does that impact both leakage and switching, etc. Kind of as an optimization problem. Okay, thanks.